All right, so let's look at this next set of problems having to do with differential equations. So I started with Newton's equation, which is a second order equation, and showed that it can be converted into a system of first order differential equations. And this is true in general, that any higher order differential equation can be converted into a system of first order differential equations. Very nice result that all you have to worry about are first order differential equations as long as you don't mind converting them into a system of equations. Right? So here I asked you to do the same process for a third order differential equation. So let's just take a look at this equation here that I referred to, and we'll see what it is. So we'll look at this. So the differential equation was down here. All right, here we go. Now here my t is my independent variable, my little t is my independent variable, big T is the dependent variable, which is my function, and then everything else here is a parameter. I said you can use delta squared as a parameter. In fact, in the original problem it's not a parameter, but in our case, in our exercise, we're treating it as a parameter. Okay, so we have these parameters. So you see you have a third derivative and a second derivative, and then you have a constant here. Right. Now the way to convert this is to convert the derivatives into variables. Okay, so you've got the, let's see, where are we here? All right, so you've got, instead of x1 we're going to say t, because that's my first function. My second x2 will be dx, dt, d capital T, d little t, and x3 is going to be d squared capital T, dt squared. Right? So in my system of equations, I'm just going to express these relations plus the equation itself. So I have the definition of x2 as the derivative of x1. I have the definition of x3 as the derivative of x2. Usually you would write the derivatives on the left-hand side because you want to write this in the form derivative of something equals something. Derivative of variables equals function of variables. Okay, just like we did up here, derivative of x1, x2 is a function of x1 and x2. So my first variable x1, which I treat as t, is the derivative is equal to x2, which is defined to be the derivative of t. Then the derivative of x2 is the derivative of is x3, which is accords with this definition. And then what about dx3 dt? All right. Well, I just go back to the equation that I have here. This one here is dx3 dt. This one here is x2. I'm sorry, this one here is x3. This one here is x3, and then this one here is x1. So in fact, x2 does not appear in this equation. It appears in the other equation, so it still has an influence. But this would be dx3 dt equals negative 1 over tau times x3 plus c over tau gamma delta squared times x1. So that would be the last equation. All right, so that takes care of number 1 here. Okay. All right, now, so the other part of this is to talk about matrix exponentials, which apply when you have a linear equation. So you have the derivative of a vector is some linear function of the vector. And you know that you can express linear functions generally as matrices. All right, now, as I said, if v was a scalar number, then you would just have this equation here, and you could integrate this and get the exponential solution, where x0 is the initial condition, right? x0 would be the value of x when t is equal to 0. Now, it turns out that you can do exactly the same thing for vectors. You just have a different definition for the exponential. The matrix exponential is defined as a power series. So you have a power series of matrices. That's okay because matrix you can multiply, so I can define these powers of the matrix. And since I'm dividing by factorials, these additional contributions get small very, very quickly. All right, so this actually does always converge, and you can always define this matrix exponential. So if A is diagonalizable, the power series simplifies tremendously. So what you do, so it shows using matrix power series that the exponential of TA is x times the exponential of dt times x inverse. So in other words, to get the matrix exponential of a diagonalized matrix, all I have to do is to exponentiate the diagonal, and then I hit it with these transformation matrices that do the diagonalization. All right, and so this exp of dt is just the eigenvalues exponentiated on the diagonal. All right, so this is actually a straightforward proof. You simply replace a in here with x dx inverse. And for instance, I have ta squared. This would be t squared times a squared. You can do that with, because these are numbers, so the numbers will commute. So t squared, a squared. A squared is x dx inverse, and the x inverse and the x in the middle cancel, and you just get x d squared x inverse. Same thing with this. This ta cubed is going to become t cubed x d cubed x inverse. Okay. Now, so all you have to do is collect all of the d cubes, all of the powers of d. Sorry, let me say that again. In every term here, you'll have an x on the beginning and an x inverse on the end. So I can take the x and the x inverse out of every term here. Okay, so I'll have x, and of course I is equal to x inverse, so I can take that out also. So I have x, and then instead of a's here, I'll have d's, and then I close my parenthesis, and I get an x inverse on the other side. So I can factor out an x and an x inverse out of every single term. All that remains is the d. Okay, and so I should say here, replace a with x, the x inverse terms in the middle all cancel, and then you also can factor out x in the front and x inverse in the back. Okay, and what remains is just is the exponential of dt. All right. Okay. All right. So and that's exactly what we wanted to show: x in the front, x dt, and x inverse in the back. Okay. All right. So I'm using there the fact that if you take a diagonal matrix and you raise it to a power, you just get each diagonal entry to that power. All right. All right. Now here I talk about eigenvalues. And suppose we have the eigenvalues ranked and d1 is much bigger than the others. Then if I look at this matrix exp of dt, then the term, the exponential of the largest eigenvalue times t is going to be much larger than the other diagonal terms. So let's specify to the case where you have just two terms, v1 and v2, two eigenvectors with two eigenvalues. Okay, and you just have, so you just write the exponential of ta on this as a linear combination of v1 and v2. Now, since this is a matrix, we have linearity, so I can write this as c1 times exp of ta times v1 plus c2 times exp of ta times v2. But remember that the way that exp of ta applies is this way. All right. Or rather, let me say it this way. If I apply exp of ta to v, if I apply x of ta to v, what do I get? Well, I put a v here. So I get v and then plus tav. What is tav? Well, since a is an eigenvector, that's going to be t times d1 times v. This is going to be t squared times d1 squared times v over 2 factorial. This is going to be t cubed times d1 cubed times v over 3 factorial. So remember, if I multiply this matrix times a vector, I'm going to get a vector. So all these terms will be vectors, but they'll all be multiples of v. If I collect all the multiples of v, I get the exponential of t d1. Same thing with v2. If I apply this matrix here to v2 and do it term by term, a on v2 is going to give me d2 v2. A squared on v2 is going to give me d2 squared v2. Then this is going to give me d2 cubed v2. I factor out all the constants. I have lots of constants times v2. Those constants all add up to this exponential. Okay. All right. So I've got this result. All right. Now suppose v1 and v2 are in the previous problem has d1 equal 1 and d2 less than 1. Find v0 and the limit as t goes to infinity of v of t. Well, v of 0, just plug in t equals 0. If I plug in t equals 0, I'm going to get c1. Now d1 equals 0 gives me a 1 here, so it's c1 v1 plus c2 v2. So in other words, if I know my initial vector, I should be able to divide it up into a sum of eigenvectors. That's a way you divide things up into the basis. Once you've divided up into eigenvectors, you can see what happens for all time, because I know that what this matrix will do to any multiple of v1 will simply multiply by this exponential. What the matrix will do to any multiple of v2 will be simply multiplied by this exponential. Now what happens when t goes to infinity? Well, this term gets very, very big, because d1 is 1. This becomes exp of t. So this term is going to dominate. This one is less big, but certainly this is going to go to infinity. This is going to be a much smaller term, right? So this is the one that's going to dominate. Actually, what I really should have said was that the eigenvector is 0, or the eigenvalue is 0, in which case this would go to a steady solution. And if I have a negative eigenvalue, this will go to 0. All right. So let me stop there, and I'll make one more video for the symmetric positive definite matrices part.